I'm Norman Wildberger. Today we're going to look at some interesting aspects of triangle geometry in universal hyperbolic geometry. We're going to look at analogs in the hyperbolic setting of some very famous triangle points in the Euclidean plane. The centroid of a triangle, the circumcenter of a triangle. And this is all based on our understanding of the midpoint of a side. So if we have 2 points in the hyperbolic plane, we know what it means for there to be a midpoint between those 2 points. And we saw last time that if a midpoint exists, which isn't always the case, then there will generally be 2 midpoints. This makes the theory quite a lot different from Euclidean triangle geometry, and we're going to see some of that today. Now, in previous videos I've claimed that this branch of mathematics is the most loveliest branch that I know, and we're going to see some evidence for that in today's theorems. Let's start with classical Euclidean geometry, some discussion of triangle centers in the Euclidean plane. We've already talked about the orthocenter. Today we're going to look at the centroid and the circumcenter. So in ordinary Euclidean geometry, these points go back to antiquity, and the centroid is the intersection of the medians. So a median is what you get when you take the midpoint of a side of a triangle, so halfway between the 2 points, and you join it with a line to the opposite point of the triangle. So that's a median. And there are 3 medians in the triangle, and they meet at the centroid, which is usually called G. And we're using capital letters for points here because this is the Euclidean setting. Now, this centroid often has a balance interpretation. It's the point on the triangle where if you put your finger underneath it, the 3 weights or masses on the triangle vertices would balance. So it's a balancing point. Another important center is the circumcenter, which we're going to denote by C. And that's also obtained from the midpoints of the sides, this time by looking at perpendicular bisectors. So we're looking at lines which are perpendicular to the sides of the triangle through the midpoints. There are 3 perpendicular bisectors, and they meet at a point called the circumcenter. Now we're going to give a different name to perpendicular bisectors. In hyperbolic geometry, perpendicular bisectors is a bit too much of a mouthful. We're going to be having lots of words as it is, so we have to try to be concise. So we're going to use instead this new term, midlines. We'll see, in fact, that the midpoints and the midlines are in duality with each other. So this is very apt terminology. Another slight point of deviation, the circumcenter C notation is not standard. It's quite common, in fact, but often in triangle geometry, at least, the circumcenter is denoted by the letter O. So after much toing and froing, I've decided that I'm going to stick with C for circumcenter. There are some good reasons for that, most notably that the term O, or the symbol O, really ought to be reserved in our context for the origin of an affine or vector space. So circumcenter C, centroid G, together with the orthocenter that we're calling H, those are the 3 classical points in Euclidean triangle geometry. And now we come to one of the most famous results in all of geometry, which is the discovery by Leonhard Euler that these 3 points were in fact always collinear. And moreover, that they were always in a certain ratio with respect to each other. That the ratio from H to G to C was always in the ratio 2 to 1. It's truly remarkable that it was only in the 18th century that this was discovered. Truly remarkable. So there's the circumcenter, which is also the center of the circle that goes through the 3 points. The centroid, the place where the 3 medians meet. and the orthocenter, the place where the three altitudes of the triangle meet. So a natural question is, well, in hyperbolic geometry, is there an analog of this? Are there centroids? Are there circumcenters? We've already seen that orthocenters exist. So do centroids, do circumcenters, and if so, is there something like an Euler line? It's a natural question. Well, it turns out that centroids and circumcenters do exist sometimes, but not always. And when they do exist, there's more than one, typically. And in fact, I know of no analog of the Euler line in hyperbolic geometry. That doesn't mean that it's not interesting, though. We'll see that there's still a lot of other interesting things that happens that compensates for our lack of the Euler line. So we need to talk about the analog of the perpendicular bisector in universal hyperbolic geometry. And that's the concept that we'll call a midline. So we'll refer to a midline of a side. A side is 2 points, and we might as well stick with the side BC like we've been talking about previously. So there's 2 points B and C, there's the line through BC. There, up here, is the dual of the line BC. Now I remind you that the midpoints of this side are the diagonal points, in this case here, of this particular quadrangle of null points, alpha, beta, gamma, and delta, formed by joining B and C to this dual point BC perp up here. So these two lines form this quadrangle, and then that quadrangle has some diagonal points obtained by joining pairs of opposite sides. That's one such diagonal point, and another diagonal point is this one here. The third diagonal point is this one here that we've already started with. So the two new diagonal points, A and D, they are the midpoints of the side BC. And we've seen that that means that if we reflect in A, or if we reflect in D, then B and C are interchanged. Now this picture allows us to also define the midlines of the side BC. Those are lines that pass through the midpoints, which are perpendicular to the line BC. That's an exact analog of a perpendicular bisector. So there's one midline. Because it passes through A and it's perpendicular to BC, it's perpendicular to BC because it's passing through the dual of BC. That's exactly the condition of being perpendicular to it. Similarly, this line here passing through D and the dual point is necessarily perpendicular to BC. So there are two midlines, this one in blue, this one in blue. And we can say a little bit more. In fact, these two midlines are nothing but the duals of the two midpoints. So I remind you of a very important fact about a quadrangle of nil points. Namely that these three diagonal points were all perpendicular to each other. That means that if we look at this line here through this diagonal point and this diagonal point, its dual is in fact this point. And the dual of this line through this diagonal point and that diagonal point is the third diagonal point, namely A. So this line has another description as simply being the perpendicular or the dual of A, and this has another description as the dual of D. So the lines A perp, which is DE, E is this dual point BC perp, and D perp, which is AE, these are the midlines of the side BC perp. In Euclidean geometry, we would call them perpendicular bisectors, and we can use this terminology also, but I prefer to use the term midline. So now let's consider a triangle. A triangle is a set of 3 points, which are not collinear. So suppose we have a triangle ABC. Then it has 3 sides. The side AB, side BC, the side AC. Now each of those sides might have midpoints or might not. So the total number of midpoints of this triangle, or of the sides of the triangle, can be as low as 0 and as high as 6. So let's assume from now on that each side has 2 midpoints. And we'll call the midpoints generally little m. So little m will be our symbol for a midpoint. And typically we're going to have maybe 6 midpoints in a triangle figure. We'll put a little m beside all of the midpoints. I won't call them m sub 1, m sub 2, and so on, because there's no perhaps natural labeling for them. I'll just call them all m. So there might be 6 little m's floating around in a diagram. They're all the midpoints of this triangle. Now the duals of these midpoints we've seen, those are midlines. So those will be 6 midlines, and we'll use capital M to denote them so that the duality between the midpoints and the midlines is clear. Right? This is an important feature of this situation that's not happening in Euclidean geometry. Here the midpoints and the midlines are actually dual, pairwise. Okay, what is a median? Well, it's just a join of one of the original points of the triangle, in other words A, B, or C, for example A, and one of the midpoints of the opposite side. So the opposite side of A is the side BC, and we're assuming that has 2 midpoints. So we can join either one of them up with A to create a median. So there are 2 medians emanating from A, 2 medians emanating from B, and 2 medians emanating from C. A natural question. Do these medians meet? Well, of course, any 2 lines meet because we're in projective geometry. But the question is, do 3 or possibly more of these lines meet? And if so, how often? Well, let's have a look at an example. So here's our null circle, and I've chosen a triangle that geometrically at least has 6 midpoints. Triangle A, B, C. So there it is there. And I've kind of drawn the interior of the triangle, interior in quotes, in green here, just to let you see a little bit more clearly where the triangle is. In my geometer sketchpad diagrams, I will often make the triangle yellow. Well, I'll make the interior of the triangle yellow, but you should be aware that that interior has really no meaning so far in our geometry. It's purely a visual aid to let you see things better. The triangle itself is just the 3 points. Of course, I also draw the lines of the triangle to make it clear. Now in this case, the 3 sides of the triangle have 2 midpoints each. For example, the side AB, here it is here, there is 1 midpoint called M, and the other midpoint is out here. The side AC, 1 midpoint M there, the other midpoint somewhere down this direction. And the third side, 1 midpoint there, other midpoint somewhere out there. Now, there are 6 medians. Where are they? Well, say from A, we can join A to this midpoint. That's 1 median right there. We can also join A to this other median over here. That's another median. And there are 2 medians emanating from B. That one there, that line, and also the line going down here. This doesn't look exactly like a straight line. And that's because this diagram is not exactly accurate. I've just sort of drawn this in by hand. In a little while I'll show you some geometer sketchpad versions of these kind of diagrams which are much clearer and more accurate. It's not so easy to draw such a thing sort of freehand and make all the things that are supposed to be collinear actually collinear. But anyway, so there is the median BM. And we've seen that other median there. And then there are 2 medians going through C, one going through that midpoint, and another one going through that midpoint. Now, the question is, do these medians meet 3 at a time? Well, yes, they do. So there are 3 medians that meet in a point there, which we'll call G for centroid. But if we keep that median and look at the other two medians going through C and A, so that one instead of that one, and that one instead of that one, then these three medians meet at another point G up here, which is also a centroid, deserves to be called a centroid. And then there's another centroid here where three more medians meet. And there's another centroid up here where three more medians meet. Again, they don't quite meet here because my diagram is not very accurate. Okay, but they ought to meet if this was a very accurate diagram. And if you make a diagram with very sharp pencil, very careful constructions, this is all constructible just with a straight edge once you've got your base circle. You can check, very good exercise, that the things do line up as I say they do. So we have 6 midpoints labeled M. We have now 4 centroids in green, one there, one there, one there, and one there. But we observe something else that's rather interesting, that the midpoints M, the 6 midpoints, actually lie on 4 lines. They're actually the points determined by a quadrilateral of 4 lines. So where are those lines? Those are the lines in red in the diagram. So for example, this midpoint, and that midpoint are collinear, as are this one, and this one, as are this one, and this one, and there's this one here, this one, and this one, a 4th line. There are no such lines in Euclidean geometry. In Euclidean geometry, there are only 3 midpoints. There's not enough of them to be able to see these other lines, at least not in the usual way of looking at things. We're going to give these lines names. We're going to call them circumlines, and we'll denote them by red. This is a very rich and important diagram showing the midpoints, the medians, the centroids, and the circumlines. Here are some Geometry Sketchpad illustrations that you can have a look at, which are more accurate and illustrate the same story in different cases. Here's a summary of those facts that I just mentioned. The meets of medians theorem. If a triangle has 6 midpoints, then the 6 medians meet 3 at a time at 4 centroids, which we'll denote by G, little g. The join of midpoints theorem. If a triangle has 6 midpoints, then these 6 midpoints are collinear 3 at a time on 4 circumlines, which we'll denote by capital C. Now this second result has a dual formulation, which is also very important, because the duals of the midpoints are the midlines. So if this is true, then it's also true that if a triangle has 6 midpoints, then the 6 midlines are concurrent 3 at a time at 4 circumcenters, little c. If you have 3 points which are collinear, then the duals of those 3 points will be 3 concurrent lines. And where they meet will be the dual of the line where the original points were on. That's duality. So it's crucial that the duals of the midpoints are the midlines. That's what's making this happen. So we now have to have another picture to show the midlines. We haven't yet seen a picture illustrating the midlines. Now we can do that. Also, we'll get to see the circumcenters appearing. So let's have a look at that same triangle, more or less. The triangle A1, A2, A3. And I'll draw the midpoints just as before. So there's one midpoint and another on that side, one midpoint and another on that side, and then on this side, this midpoint and the one down there. More or less in the same position as the other one. Okay, now we're going to look at midlines. So these are the same as the perpendicular bisectors. There's one going through every one of the 6 midpoints. So this one here, for example, going through that midpoint there, it's got to be perpendicular to this line. So it's got to go through the dual of this line, which will be right here. And the midline passing through this one will also be dual to this line. So we'll also go through the dual of this line, which is this point here. So that's one midline. That's another midline associated to those 2 midpoints. So the midpoints on this line, there, that M and that M, will have associated midlines there and there. And finally, the midpoints on this line, that M and that M, have midlines, this one and that one. So the dual result that we mentioned at the last slide says that these midlines are also going to meet 3 at a time at 4 points, which are the circumcenters of the triangle. And they're in red, denoted with a little c. So here's one place where 3 of those midlines are meeting. Here's another place where 3 of those midlines are meeting. Here's another place where the 3 midlines are meeting. And here's another place where they meet. In fact, these 3 lines meet sort of down a little bit off the page. That typically happens in these pictures. Often it's hard to fit everything onto one page. But you can still sort of see the existence of meets off the page. It's quite a nice picture because there are 4 circumcenters. And I remind you once again, I emphasize the point that this is all prior to any metrical constructions. We have not defined notions of distance or angle or analogues of them, which are quadrants and spread, in our formal setting. Yes, I've mentioned them earlier when we were connecting with cross ratios, but in our sort of formal setting up now of this theory, we have not yet introduced those things. So we are still in the position, however, of being able to talk about circumcenters, midpoints, centroids. The other thing to observe is that in classical hyperbolic geometry, the whole picture is all inside this disk. So everything outside here is completely invisible. And so there, in particular, there's only one centroid. There's only one circumcenter. In fact, the circumcenter doesn't always have to exist. So just as we saw that in classical hyperbolic geometry, the orthocenter doesn't always exist. Sometimes it does, but sometimes it doesn't. Depends on the triangle and its position with respect to the circle. Here it's exactly the same story. In this case, this triangle does have a circumcenter that's visible, but if I moved them around, if I made it more of a slanty triangle, I could easily create that circumcenter to go outside, and then in classical hyperbolic geometry, it would be invisible. Which again is why in courses on the subject, if you take a course in hyperbolic geometry at a standard university, it's not a theorem that the perpendicular bisectors meet and form a circumcenter. That's not a theorem. It's just a happy accident that occurs some of the time. Here we see that it's all because this constrained view sticking inside the circle is far too limiting. You have no hope of seeing the whole story. It's just a small part of this bigger picture. And the bigger picture is very rich and influences what's going on inside there too. Okay, but the story gets richer now when we combine centroids and circumcenters in the same picture. The results that I've shown you so far have been known by classical geometers in some sense. Now I'm going to show you some theorems which I believe are new and little short of spectacular, really. They concern what happens when we put the centroids and the circumcenters of a triangle together. Look at them all at once. So here's a triangle, more or less the same one that we've been talking about, which has 6 midpoints, 2 there, 2 there, 2 there, and therefore it has 4 centroids, 1 there, 1 there, 1 there, and 1 up there. And it has 4 circumcenters, 1 there, 1 there, 1 there, and 1 there. Now the theorem states that the 4 centroids and the 4 circumcenters correspond by association with the same triples of midpoints. What does that mean? So it means that, let's say we look at this this centroid here. Okay, that's the meet of 3 medians. Medians associated with these 3 midpoints. Out of all 6, we take these 3 midpoints to form that centroid. Well, if we take those 3 midpoints and form the midlines through them, the midlines through them give us that circumcenter. So that particular centroid and that particular circumcenter are both associated to that triple of midpoints. Similarly, the other centroids and circumcenters are associated to triples. For example, this one here is, okay, it's that median there, and it's, which other median? And this median here, and this median here. So it's associated to this midpoint, and this midpoint. This one, and this one. So basically we've taken these 3, kept one of them fixed, and moved the other 2 to the opposite midpoint on the same line. Always changing 2 out of the 3 midpoints. Okay, so there's a natural association. That's why I'm allowed to label them G1 and C1, G2 and C2, G3 and C3, and G4 and C4. We can pair them up, like match them up, like have a date between the centroids and the circumcenters. Okay, but more interesting, the joins of these corresponding pairs meet in what we call the Z point of the triangle. So if I join up now G1 with C1, I get a line. If I join up G2 with C2, I get a line. If I join up G3 with C3, I get a line. If I join up G4 with C4, I get a line. And all those 4 lines meet in one point. That point, we're going to give it a name. It's a very interesting point of the triangle. We're going to call it the Z point of the triangle. Now, at this stage it looks like, well, that point's only going to be defined if the triangle has midpoints. But it turns out, we'll see later on, that this Z point actually has another definition, which in some sense is more fundamental than this one. So it turns out that every triangle has a Z point, whether or not it has any midpoints. Okay, you'll just have to take my word for that for now. But at least in this situation, the Z point is an interesting object. So why is that Z point interesting? Well, it has some other remarkable properties. So here are 2 more theorems about this Z point. The first is the Z point ortho-axis theorem, which states that the Z point of a triangle, if it exists, lies on the ortho-axis. I remind you that the ortho-axis of a triangle, say in this case here, is the line joining the orthocenter and the orthostar. That's the line that I claimed was the most important line in hyperbolic triangle geometry. And here we see some evidence for that. This new point, the Z point, lies on this line. And in this triangle here, I've given you indication. We already know that besides the orthocenter and the orthostar, also the base center point also lies on the ortho-axis. Now we have a fourth point, the z point. And we have another theorem, the ZBHS harmonic range theorem. We now have 4 points on this ortho-axis. The z point, the base center, the orthocenter, the orthostar. And the claim is that the points Z, B, H, S, those 4 points, form a harmonic range of points on the ortho-axis. So in other words, B and S are harmonic conjugates with respect to Z and H. Or Z and H are harmonic conjugates with respect to B and S. In particular, if you know 3 of them, you can calculate purely with the straight edge where the 4th one must be. Now, okay, eventually we're going to want to prove these things. And proving them, as you can imagine, is a computation. But it requires a rather careful setting up of an algebraic framework in which we can make calculations readily. So we're going to do that, of course, as time goes on, but it's not really the first order of business. The first order of business is for you to get some visual, physical intuition about results like this. So what I'd like you to do, if you can, is to try to verify this theorem in some special cases. It's going to require some patience, but it's a very satisfying thing. You get a nice circle, a very sharp pencil, straight edge, spend an afternoon drawing some triangles, midpoints, orthocenters, orthostars, everything just with a straight edge. Sharp pencil, maybe a few different colors, and you can verify this. It's very satisfying to do. Okay, you can verify it with a pencil and paper. And you can, I hope, get an appreciation for the marvelous aspect of these results. Especially these 2 results. They're really fabulous, I think. Next time we're going to get at this alternate way of thinking about the Z point, which I hinted at. We're going to look at parallel lines in hyperbolic geometry. This has been a very big bugbear in the theory classically, and historically it's almost been a red herring, this discussion and pursuit of the parallel postulate. And I really have to reconfigure people's thinking about parallel lines in hyperbolic geometry. So next time we're going to do that. So be prepared to think in a new way parallelism really means in hyperbolic geometry. When we do that, we're going to discover a lot more interesting things appearing. In particular, we're going to discover what the Z point really is. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.